So, welcome to 65 lecture on network analysis, and we have seen that how graph analysis can be utilized to solve a network problem completely by using the loop analysis method. Similarly, we can solve the same network problem by nodal analysis. So, we started with this, you recall that this is the general element and this is the thing, and this portion I will just delete and straight away write that this is the basic equation, which will be this one. This I will erase, not necessary. So, so this was the kth element of the network, and this time I have decided I would like to apply the nodal method. That is, I will invoke A matrix, that is the where we write the KCL equations at the node A I is equal to 0. What are the two relations there? These are the two relations, terminal relations I will utilize. I into I E is equal to 0, and A transpose into V nodes is equal to V E, element voltages. These are the two relations we will utilize. So, so finally, by nodal analysis your target is to find out what are the node voltage of the circuit. If you have got that, you have solved the circuit. So, once again we come back to this equation. So, first thing is I will apply KCL. So, this equation, this is true, we have already got it, and then I will say that this j d k into I e k, this portion you can erase. So, this is the thing, V e k is equal to this one, this is equal to V e k. Forget about this. So, this is the thing I have got, j d k I e k, j d k I s k plus V s k. So, j d k I e k can be written as V e k minus z e k I s k minus V s k, is not. Then what I am going to tell, that this is true for all the elements k equal to 1 to 6. Then this essentially means that okay, before that what I will do. So, I e k I want to find out, what I will do, I e k then will be equal to 1 over j d k divide by j d k into V e k minus only I s k, j d k will cancel out, minus V s k by j d k, divide both sides by j d k. But this j d k reciprocal of impedance is admittance. So, this can be written as y e k V e k minus I s k minus y e k into V e k. This is the thing. So, this equation is the equation of interest when you want to find out the node voltages. So, this you copy and paste next page. Oh, sorry, delete. So, I will copy this one. So, from this I got this. Okay. So, IEK is this one. From this equation I got this equation. Now, what we will be doing is this thing, that is, this was at the top, then we also got this. So, from this to this I get. Now, this equation I will write it as IEK or IEK is equal to YEK VEK minus ISK minus YEK VEK, and in the same way it can be written in a matrix form as a column vector comprising of all the element currents can be written as a diagonal y into a column vector comprising of element voltages minus a column vector of source current of all the elements minus y, it will be another admittance matrix into V. What is y? Y is nothing but YE1, YE2 dot YE6 for this particular problem. These are all 0 elements. What is YE1? 1 by ZE1 and so on. Therefore, this is the basic equation we have got here. Now, in nodal analysis method, you have to apply KCL. So, multiply both sides by A, matrix A. So, if you pre-multiply both sides with A, you will get A into IE is equal to A into Y into VE minus A into IS minus A into Y into VE, but A into IE is equal to 0. This quantity is 0, Kirchhoff's current law. So, this is equal to a column 0 vector, is not? Therefore, we can say that this is the AYV minus AIS minus AYVS equal to 0. Therefore, I can say A into Y into V will be equal to A into IS. You take these two terms on the right hand side plus A into Y into VE, that will be the thing. But what is the target in nodal analysis? To find out the node voltages, is not? So, we know that in nodal analysis, these two we have already established, A into I equal to 0, that we have already taken care of, we have used that information. And then the second one is A transpose into V node voltages is equal to your element voltages. So, this for V here I can write A transpose into V n in this equation. So, it will look like A into Y into A transpose into the node voltages, that is what I want to find out, will be equal to A into I s minus plus A into Y into V s, this will be V s, this will be V s. Here I wrote wrongly, I s k, this will be V s k. Sorry, please correct that, otherwise you will be under V s k. V k s I s k. So, this is V s k. Source you take on the right hand side, V s here, this is V s. So, this will be V s. Here this line, So, anyway, so take that correction. So, A y A transpose into V n is equal to right side only source current and source voltage. Okay. What is y? Y is this diagonal matrix, very easy to form. Give the network, I will in no time make this matrix available to me. I can also form the A matrix by drawing the graph, directed graph, only plus 1 minus 1, I will do that. Then this whole thing will be a square matrix, and it is called the like loop impedance matrix, earlier we called, it will be node admittance matrix, people call it, node admittance matrix. May be replaced by another symbol capital Y or so on, and take inverse, multiply with this, you get the node voltages. Then I am telling, if you know the node voltages, you have solved the circuit. Why? Because after you get the node voltage, you can easily find out the element voltages. After getting V n, that is this one, by solving this network, multiply with inverse on the both the sides, you will get node voltages. If you get node voltages, element voltages can be easily calculated. V is equal to A transpose into V n. Element voltages across each element, these voltages are known. And if you know element voltages, for example, if I know V 1, this voltage is known, what will be I e k? You can just subtract the appropriate source quantities in column form, or individually take the equation, find out I e k. Got the idea? So, the current flowing through the impedance Z d k is I e k plus I s k. So, I will add up with that. So, this is the in nutshell, you have to do now these steps after establishing these fundamental relations A I E. is equal to 0, A transpose into V n equal to V. Then we arrived at this equation, where on the right hand side only this column vector I s and V s are known. The good news is not all the V s and I s will be present. It is very unlikely in all the elements you have sources. Okay, whichever elements is there, I will put those numbers, and in whichever branches sources are not there, I will put zeros there. So, 0 entries will be there, and Y is a very simple matrix. So, I can easily write down a program to find out V n node voltages of the given network. And as you know, if you know the node voltages, you can easily calculate the element voltages. If you know the element voltages, you know everything in the circuit. You can find out whatever. If you know this element voltage V e k, I want to find out this current. What will be this current? I e k, I flowing through Z d k will be how much? I Z d k will be element current I have found out, I e I j d, any branch column vector. It will be simply this one, I e will be J I e element current vector plus I s, is not. So, once you get V, we will be able to solve for these two. This is in nutshell this thing. You have got the element voltages. If you know the element voltages, element voltage is nothing but V e. If you see element voltages, this is of course in impedance term, you can easily work out how this relation will be by looking at this diagram. So, this is another way of solving the circuit by loop analysis. I do not know, I will don't have much time to complete that. What I mean to say, let us take some numbers and to fill up these matrices. Suppose you have a network like this. An example, suppose you have got a network like this, 5 ohm, this is 8 ohm, no current source there, here is an element, here is another impedance, this is say 4 ohm, and this is this impedance I have shown. It could be any other impedance in Laplace domain also, it does not matter. So, this is 4 ohm, it is like this, and here is an element which is 7 ohm. There is here I should change it. Here there is a source here, say plus minus 2 volt is there. Here there is no source, and here is 1 where there is no source, and there is an current source there, say 2 ampere. And this branch is having only impedance, suppose any arbitrary I am drawing, and here is one resistance only, say 6 ohm. Acha, this network, these are the nodes A, B, and this is the big node C. It has, let us say this is 2 ohm. In this network, while drawing the graph of this network, what I am telling, A, B, this is 0 say, this is say C, you just draw single line. Here also single line. There were although 2 elements, 5 ohm and 2. Here also a single line, 4 ohm. here also a single line. Now, between this C and O, there is a resistance in parallel with a current source. While drawing the graph, I will just draw like this. That is what I am telling. Here actually this 2 ohm and this thing, and here is 6 ohm, and here you do not show any values. Now, what I am going to do? I want to make a directed graph of it. So, this is the graph of this network, and then I will say that okay, call it arbitrarily, this is 1, this is 2, this is 3, this is 4, this is 5 and this is suppose 6. I have directed the curve. Then let us say suppose this is 1 ohm. I want to make JD matrix. It will be a 6 by 6 matrix 1, 2, 3, 4, 5, 6. Okay. What will be this entry? 1, 1. JD2 will be 5. JE3, this one 3 I called, 6. What is JD4? 4. This is the impedance. Where is JD5? 7. And where is JD6? That is 2. And your Z impedance matrix has been formed. Got the point? Suppose I want to make the column vector of the sources Vs. What should I do? Column vector will be all the source voltages present in all the elements. Start with element 1. Is there any source voltage? No, 0. It will be a column vector. 2. Source voltage is there? Yes, it is there. With this about sign you point note, this is plus, this is minus. What is the arrow given? This way. So, this is fine, plus 2. What about and in this will be a column vector. So, this will be 2 here, and in no other elements voltage sources are there. So, 2, 3, 4, 5, 6 Vs is there. Similarly, what will be Is? Another column vector. In all the elements current is present, current source is present. In one, no current. 2, 3, 4, 5, only current is in the 6th element. So, 0, 0, 4, 5, 6th element current is 2 ampere and it is plus 2, I will write. Plus 2, and this is your Is. And then A matrix, if you remember for this particular problem the way directed graph has been drawn, A will be in the meantime this is JD. What will be the admittance matrix? It will be just reciprocal of these numbers 1 by JD, that is it will be 1 by 1, this will be 1 by 5, this will be 1 by 6, 1 by 4, this is 1 by 7 and this is 1 by 2. This will be your admittance matrix. Then A matrix will be needed. A matrix is very simple. What? At each node KCL. How many elements will participate in deciding KCL? 6 elements. So, here I will write it nicely here. So, this will be A matrix, for example, will be this one. So that you get a feeling of this. So, 1, 2, 3, 4, 5, 6. and here this is the column matrix I1. In fact, this need not be written to write down I4, I5, I6. These are the 6 elements, and here A, this is junction A, B, C nodes. So, all currents are coming out, 1, 2, 3 are positive, 1, 1, 1. For others are zeros, A. Similarly, at node B, 4, 5 are coming out, so plus, plus, and 2 is minus, 0, 0, 0, and finally, at node C, 6 is coming out, 6 is plus, 3, 5 are minus, minus. A matrix is ready. Now, the question is how to find out the B matrix? Okay, to find out the B matrix, you have to draw a tree, is not? Then find out fundamental loops there. So, that B matrix depending upon the tree you draw, identify the loops and then apply KVL in those loops, fundamental loops, and get B matrix. So, I stop here today, and we will continue with this, that is the third method, which is called the cut set matrix method, and give you some example. I will try to upload some solved problems in my website. Thank you.